Have you ever wondered why changing just two simple numbers on an MRI scanner completely changes the image? Well, welcome to the Explainer. Today we are tackling a subject that almost every radiography and medical student dreads at first, but one that is absolutely fascinating once it finally clicks: MRI physics. Those two magical numbers are TR and TE. They are literally the absolute backbone of MRI image contrast. And yeah, I know exactly what you're thinking: physics, equations, endless memorization. But I promise you, by the end of this explainer, you are going to understand TR, TE, T1 weighting, and T2 weighting intuitively. We're going to ditch the confusing textbooks and focus on pure visual understanding. No memorizing definitions required. So here's our roadmap for today. We'll start with a quick look at hydrogen protons. Then we'll break down exactly what TR and TE are. After that, we'll see how they work together, look at some real clinical applications, and finally, wrap up with common mistakes and a few killer memory tricks.
All right, Section 1, what are hydrogen protons? Okay, before we touch any MRI parameters, let's set the stage. Our bodies are basically 80% water, right? And water is made of hydrogen and oxygen. Well, those little hydrogen atoms are the absolute stars of the MRI show. You can think of these hydrogen protons as tiny little bar magnets. When a patient slides into that massive magnetic field of an MRI scanner, which, by the way, can be 30,000 times stronger than the Earth's gravitational field, these tiny human magnets align with the scanner's field. And they don't just sit there. They wobble or precess around that magnetic axis, kind of like a spinning top. Now, to actually get an image, the MRI scanner sends in a burst of energy called a radiofrequency or RF pulse. This pulse essentially knocks those wobbling protons down into a high-energy state. We call this excitation. But here's the catch. The scanner doesn't leave the pulse on. It turns it off. And when it does, the protons naturally want to stand right back up and return to their normal, relaxed alignment. This recovery process is called relaxation, and it's actually during this relaxation phase that the protons give off the signals we use to create the MRI image. Which brings us to Section 2, what is TR, or repetition time? Okay, think of it like this. Imagine you fire a starting pistol, and a group of runners takes off. The TR is simply the amount of time you wait for those runners to walk back to the starting line before you fire the pistol again to repeat the race. In MRI terms, TR is the time we wait for our tissues to recover their magnetization after that first RF pulse, right? Before we repeat the process and send in the next pulse. Now, what's really cool is how different tissues recover at totally different speeds. Think of fat tissue as a world-class sprinter. It snaps back to the starting line incredibly fast. Water, on the other hand, is more like a tired jogger. It takes a really long time to get back. So if we choose a short TR, meaning we fire that starting pistol again really quickly, the fat is ready to go, but the water is only halfway back. Because the fat is fully recovered, it gives us a massive bright signal, while that unrecovered water gives a dark, weak signal. And that is exactly how a short TR creates a T1 weighted image. It purposefully catches the tissues while they're separated to highlight their differences. Let's move on to Section 3. What is TE, or echo time? So if TR is all about waiting for recovery, TE is all about waiting to listen. Imagine you strike two different bells with a hammer at the exact same time. One is a small, heavy bell that rings sharply but fades out almost instantly. The other is a huge, resonant bell that just keeps ringing and ringing. TE is simply the time we choose to wait before we open our ears to listen for the echo or the signal coming back from the tissues. And you'll see that the signal of all the tissue starts decaying the very moment that RF pulse is turned off. We call this T2 decay. Fat stops ringing very quickly, but watery fluids like cerebrospinal fluid keep ringing for a long time. So if we choose a long TE, we're waiting a long time before listening. By the time we finally listen, the fat has gone completely quiet, but the watery fluid is still ringing loud and clear. That long wait time leaves only the slow decaying tissues to produce a bright signal. And boom, that is exactly how we get a T2 weighted image. Section 4. How TR and TE work together. This is where it all comes together. Let's decode this matrix so you literally never have to memorize it again. To get a T1 weighted image, you want a short TR to catch the differences in recovery between fat and water, and a short TE so you listen immediately before that T2 decay ruins the contrast. Short and short equals T1. Conversely, for a T2 weighted image, you want a long TR so everything fully recovers and T1 differences are completely erased. Then you use a long TE to wait for the fast-decaying tissues to fade out, leaving only the long-ringing water. Long and long equals T2. And finally, proton density. If you use a long TR to erase T1 differences and a short TE to listen before T2 differences even happen, you've essentially removed both T1 and T2 effects. The only thing left determining the brightness is literally just how many hydrogen protons are physically packed into that tissue.
Section 5. Real clinical applications. Let's see how radiographers actually use this.
The crucial point here is comparing these two brain images. On the left, we have a short TR, short TE sequence, our T1 weighted image. Notice the fluid-filled spaces in the middle of the brain. The cerebral spinal fluid is dark. T1 is fantastic for looking at normal anatomical structures because fat is bright and fluid is dark. Now, look at the right. This is a long TR, long TE sequence, a T2 weighted image. That exact same watery fluid is now glowing bright white. Why does this matter clinically? Well, diseased tissues, like tumors or areas of inflammation, usually have a much higher water content than normal tissues. So T2 weighted images act like a spotlight for pathology, lighting up that extra water like a beacon.
Section 6. Common beginner mistakes and memory tricks. Before we wrap up, let's tackle the traps almost every student falls into. First, do not mix up your controls. TR controls T1 weighting, TE controls T2 weighting. Second, please don't try to just memorize short T1, long T2 without knowing why. When you get nervous at the scanner, rote memorization fails. Instead, visualize the runners recovering for TR and the bells fading out for TE. Also, watch your terminology. T1 is the relaxation time of the tissue itself. We can't change that. TR is the repetition time on the machine. That's the knob we control to exploit the T1 of the tissue. Don't confuse relaxation time with repetition time.
To lock this in permanently, use these simple tricks. Whenever you see TR, immediately think time before repeating. It is literally the time before the machine repeats the RF pulse. And whenever you see TE, think time before the echo. It is the time the machine waits before listening for the echo. If you root yourself in these straightforward definitions, the physics will always make sense.
If you can master TR and TE, you have genuinely cleared the biggest, most intimidating hurdle in all of MRI physics. You now know these aren't just random numbers, they are precise timing tools that let us manipulate microscopic magnets in our bodies to reveal anatomy or disease. Which leaves me with a final thought for you. What other invisible forces in the human body do you think we can reveal simply by changing the timing of a magnetic pulse? Let me know your thoughts down in the comments. And don't forget to subscribe for more beginner-friendly MRI explainers. Thanks so much for learning with me today, and I'll see you in the next one.